Okay, we are live.
Okay. Good morning, everyone. I am Abhishek Roy, Assistant Professor of the Department of Civil Engineering, Meghnad Institute of Technology. Will conduct today's session along with Professor Saurabh Pal of our department. I, along with Professor Saurabh Pal, take the opportunity to welcome you all on behalf of the department. Now, I request Professor Biswajit Thakur, Professor of our department, to say few words and also to introduce the speaker.
Good morning, everybody. Myself, Professor Biswajit Thakur, would like to welcome you all to the fifth session of our continuing webinar series, Spectrum Civil Engineering today. It is because of you participants and our distinguished speakers that the program of this webinar is being a huge success and giving us courage to continue arranging such programs beyond our day-to-day campus activities. Civil Engineering Department, Meghnad Institute of Technology, is completing almost its 2 decades in the field of civil engineering education and teaching. And the students from this department are doing excellently well in both academics and industry. And today's speaker, Dr. Kaustav Chatterjee, Assistant Professor, Department of Civil Engineering, IIT Roorkee, is an example of that. It is no greater pleasure for a teacher to introduce a successful student. Let me welcome Professor Dr. Kaustav Chatterjee as our distinguished speaker today in this fifth session of our webinar series. The topic of his discussion will be numerical modeling in geomechanics. Dr. Chatterjee is an assistant professor in the Department of Civil Engineering, IIT Roorkee, since 2016. He has done his BTech from this very institute, Meghnad Institute of Technology, Kolkata, in 2010, and completed his MTech and PhD from IIT Bombay. He was a postdoctoral research scholar in Kyoto University, Japan. He is a recipient of the Best PhD Thesis Award from IIT Bombay, Professor G. L. Leonard's Best Thesis Award from Indian Geotechnical Society, Professor John Carter Award for Young Researchers from IACMAG USA, and the ISSMG Foundation Grant UK. Dr. Chatterjee is currently supervising 3 students for PhD at Indian Institute of Technology, Roorkee, and has already supervised 7 MTech students. He has authored more than 15 research papers in various reputed STI index journals and published more than 20 papers in reputed conferences. His research areas primarily include geotechnical earthquake engineering, foundation engineering, numerical modeling, soil dynamics and liquefaction, which is of significant importance in earthquake-prone areas. Dr. Chatterjee is also having membership of various professional societies like Life Member of Indian Geotechnical Society IGS, Life Member of Indian Society of Earthquake Technology ISET, Member of International Society for Soil Mechanics and Geotechnical Engineering ISSMGE. He is also an associate member of American Society of Civil Engineers ASC and life member of the Indian Science Congress Association. Apart from this formal introduction, Professor Chatterjee has been my one of the dearest students, and it is wonderful to see him doing so well in his professional career. I wish him all the best for future. This program would have been never possible without the active support from our departmental head, Professor Sheikh Hasim, who is due to some personal reasons couldn't attend this session, and of course, Professor Dr. Ankur Ganguly, the principal of Pengnasha Institute of Technology. They have extended all their support and infrastructure to make the program a success. Without much delay, let me hand over the session to Professor Chatterjee. This is a homecoming for him. I know he is enjoying the session. Dr. Chatterjee, Kaustav, the session is yours now. Thank you.
Okay. Okay. Thank you, Professor Thakur, sir, for this warm introduction, and I really feel happy to at least give a lecture in my BTech college, the place where I did my graduation from, and truly speaking, something that which I am today. Okay, so I will now start with my presentation. That is the numerical modeling in geomechanics. And I would like to thank Spectrum Civil Engineering today, that is being organized by the Department of Civil Engineering, Meghna Institute of Technology. And it's really a good thing, this webinar series that they have organized, because in this way, we have been able to come across the research that has been carried in different parts of the country. Now, come to the introduction. What is actually numerical modeling? Now we are having geotechnical structures, be it a foundation, be it a slope, a retaining wall, anything. Now when these geotechnical structures are subject to different types of loading conditions and we have to analyze them, it can be done in two different methods. One is called physical modeling and second one is numerical modeling. Physical modeling, as the term suggests, that basically involves the laboratory experiments that we are performing in the lab or the field tests. The lab test can be 1G test or it can be also a centrifuge test, that is, it has been done under NG conditions. Okay. Now, physical modeling, although it gives the reliable results, but it has certain disadvantages. Firstly, sometimes it will require labor. Secondly, the apparatus, the equipments, it is not always possible to get the same. And another important is the location, I mean the requirement of spaces. So if you are performing any field test, so what happens? Because of these difficulties, now researchers are moving towards the numerical modelings. Now, this numerical modeling can either be classified as an analytical method or a numerical. Say if you're having any problem that is related to the conventional assumption of geotechnical engineering, that is, soil is assumed to be homogeneous, isotropic, and all these things, or if the problem is having a defined boundary condition or a constant geometry, then obviously we can go for any analytical methods. However, if it is having a complex geometry, or if the boundary conditions are not constant, it is changing at different points, then obviously we can have governing differential equations. But solving these differential equations by an analytical method is not always easy. So that's why what we do, we resort to the various numerical methods that is available, and this is influenced by, as I said, the boundary conditions, the geometry of the problem on the domain and the considerations, then what are the different assumptions that is related to my particular problem. Okay, these are some of the influencing factors. Now, in this particular lecture, I am going to throw light on three different topics, that is pile response in liquefiable soils, pseudostatic analysis of sheet pile under surcharge loading, and response of caissons or the well foundations to seismic loadings. And for all of these cases, I have gone through the numerical model. It is how numerical modeling is helpful in accessing these three type of problems which are considered. Now I go to the first topic, that is pile response and liquefiable soils. And my acknowledgement, it goes to my MTech plus PhD supervisor, Professor Dipankar Chaudhary from IIT Roorkee. Now, coming to a brief introduction, is what is pile foundations. Something is always known to us that generally it's a type of deep foundations that we use in onshore and also in offshore constructions when the topsoil layers are either soft or loose and of a swelling type and they do not have adequate bearing capacity. Okay, and we have to transmit the load to a deeper soil layers where the bearing capacity is sufficiently high, and in those cases we go for a pile foundations. Now, if we are having this pile foundations in an earthquake-prone area, okay, where the water table is also at a pretty shallow depth, then what will happen? Under this dynamic loading, it will be affected or subjected to soil liquefaction. That is a phenomenon in which a mass of saturated, loose, questionless soil loses its shear strength and it will start flowing like a fluid under the action of this dynamic loading. Okay, so that's why liquefaction is a very vital condition in any geotechnical earthquake injury related problems. And there are severe factors like the input ground motion, the free field conditions, what is the response of the superstructure, then the soil pile superstructure interaction, and also the pile soil pile interaction for a pile group. This has a very important role to play in this liquefying soil during an earthquake conditions. And further, like if you're having an epicenter of an earthquake at a far off place, then this seismic motions that is traveling from the bedrock to the surface is highly influenced by the soil strata located at those places, and this has been observed in Kolkata during 2015 Nepal earthquake, whose epicenter was around 1000 kilometers away. And because of this factor, which is called the path effect, its influence was also felt in the city. So now I go to the typical soil spring model that I have considered for my present study for the seismic analysis. I've got a pile of total length 10 meters. Okay. This pile is embedded in a two-layered soil deposit. The top layer is a liquefiable sand layer, and this bottom layer is a non-liquefiable stiff clay layer. Thickness of the top layer is L liquid and this is L NLIQ. Okay. Now, this pile is subjected to a vertical load, capital P, and depth-wise variation of lateral load, which is given by this magnitude of H1, H2, like this HI and HN. Okay. Now, the soil is there. Now, because of this effect that under input seismic motion is applied at the ground surface. Because of this seismic motions, what will happen in the free field conditions? In the free field conditions, there will be some displacement of the soil. Now, this is the maximum soil displacement profile that has been observed to take place in this liquefiable soil layer. Actually, truly speaking, in this liquefiable soil layer, the displacement will be much more as compared to non-liquefiable layer. Okay, so this is, I'm assuming this to be the maximum soil displacement profile, which is not actually straight, but it's linear, it's a curved in nature. Now, now, how are these lateral loads being generated? These lateral loads are being generated from the maximum horizontal acceleration profile. That is, we have done a ground response analysis, that is an equivalent linear ground response analysis under free field conditions, and at different depths we have determined what is the maximum horizontal acceleration. Now, using this maximum horizontal acceleration and as per the standard codes in practice, that is, we have obtained the lateral load at different depths. Also, you can see one thing, that the top ground surface has been inclined at an angle of 4.8 degree with respect to the horizontal. Why? So as to generate the lateral spreading that is going to occur once liquefaction starts. So with all these input parameters, that is this displacement profile, the maximum horizontal acceleration, the vertical load, the increase of the ground surface, with all these things, the governing differential equation has been written. It is given in this particular manner. EPIP d4y dz4 plus P d2y dz2 plus eta h into d into y minus yg is equal to 0. EPIP is the flexural modulus of the pile, y is the deflection, z is the depth, P is the vertical loading, eta h is called the subgrade modulus, and y is the d is the diameter of the pile, and yg is the permanent horizontal ground displacement profile with depth. That is how my ground displacement is varying along with depth, and this has been given by the Japanese researcher Tokimatsu 1999 using this particular correlation, that is yg is equals to gx into cos of this particular term, where L liquefiable is the depth of the liquefiable soil layer and L non-liquefiable is the depth of the non-liquefiable soil layer. Now, if I solve this governing differential equation using any of the numerical method, you will have this particular solution where alpha, beta is given by this particular terms, okay, lambda is given by this particular term, as lambda square is given, and zeta is given by this term. Okay, that is zeta is, as we can see, that zeta is a function of my subgrade modulus, diameter of the pile, ground displacement, flexural modulus, liquefiable, non-liquefiable soil layer depth, liquefiable soil layer depth, and also P, what is P? P represents the vertical load that is acting on the ground surface. Now, next, what have I done? Now, this entire pile, I have discretized it into small number of elements of equal height, say small h, and I have taken one element as given over here, who's having 2 degrees of freedom per node, because I have taken 2 degree of because I have taken a 2D problem over here. That is translation yi and theta I represents the rotation component over here. Similarly, at the bottom node, theta I plus 1 and yi plus 1. This is at z equals to 0 and this is at z equals to h. And this particular node is subjected to the soil reaction from the current. And this is the degrees of freedom of a typical soil pile element that I have considered. And this represents whatever I have drawn in this particular figure over here. To make it simple, I have drawn this schematic sketch of the pile passing through a liquefiable soil with the water table on the ground surface. Now, in order to do this work, there are certain assumptions that have been considered in literature. Firstly, this one, which I have already done according to Tokimatsu, how we determine the permanent horizontal ground displacement profile. Okay. Next is, in case of a liquefiable soil, the subgrade modulus, it undergoes degradation. Why? Because in case of a liquefiable soil, the shear strength of the soil is almost equal to 0. Because my effective stress is equal to 0, and we know from Morse theory, my tau, the shear strength, is a function of my effective stress. So my eta h equals to eta hn into SF, where SF is called the stiffness degradation factor, which varies from 0.001 to 0.01 as per Ishihara and Kubrinovsky 1998. Okay. Now, eta hn is the modulus of subgrade reaction for a non-liquefiable soil as proposed by JRA and given by this term is a function of the pile diameter, the SPTN value, and the modulus of deformation. So once I know eta hn, and if I multiply it by the stiffness degradation factor SF, we will be left with eta h, which is the subgrade modulus for the liquefiable soil. And this is how we have done. These are the assumptions now. After taking in this equation and then taking a constant pile element, okay, and after giving the boundary conditions, we have got this matrix. That is how to determine the integration constant, because there are 4 unknowns. So 4 by 4, 16 unknowns will be there. And we see that this particular matrix is a function of all the parameters of the given problem. That is my liquefiable depth layer, non-liquefiable soil layer thickness, the diameter of the pile, and all the term that is given in this term of zeta. Now, what is my main target? My main target is to determine this integration constant, that is 16 integration constants, which has been done by assuming a typical stiffness approach. That is, if I consider one particular node and assuming that we are having an unit displacement over here, say, if I take this particular figure, Okay, taking this particular node over here, I am assuming that I am giving an unit displacement. So if an unit displacement is given over here, the rotation over is equal to 0, and also in the other node, both displacement and rotation is equal to 0. Similarly, in this particular node, I'm giving a unit rotation. Then displacement is equal to 0 over here, and at the bottom, both displacement and rotation is equal to 0. In this way, I have taken this particular node, and based upon this only, I have written this particular matrix over here. Fine. Now, my next thing is how I can determine the element stiffness matrix. So, K1112 with the proper symbols is given by this expression is equals to EPIP into this term into my C matrix, which I've already obtained in the previous step, plus this matrix. So, what we have done is that the element stiffness matrix that have been obtained for each element at various nodes that have been arranged sequentially or assembled sequentially to obtain the global stiffness matrix. Okay. And after doing the global stiffness matrix, and if I know what is the lateral load vector H from the ground response analysis, I can determine my delta, that is nothing but my displacement at various nodes and also the rotation at various nodes. So once I know the displacement and rotation at various nodes, what I can do is that I can determine the moment and the shear force of the individual pile elements using the computed displacement rotation, that is I'm transferring from the node to the particular element. And hence I determine what is my force, the shear force, and what is the bending moment at each various steps. So typical stiffness, FEM based stiffness approach that I have carried out for this particular study. Now we know that for any numerical work, then that work has to be validated with some existing work in literature. So what I have done is that the same model that I have discussed over here, I have prepared the same numerical model in flat 3D computer software. That is it's a finite difference based computer program by you have to write your own code for this three-dimensional problem. I assumed a free-headed pile with a floating tip, and this is the top layer represents the Nevada sand layer, and this represents cemented sand layer. Actually, the properties of this top liquefiable and bottom non-liquefiable soil was taken from Uptown's 2003 paper that was published in ASC, where they have performed a dynamic centrifuge test. So the entire dimensions of the pile soil model was taken from there, and similarly to initial lateral spreading due to liquefaction, this was incurred an angle of 4.8 degrees with respect to the horizontal. Now, Moore-Kula model was used to modeling the cemented sand layer at the bottom, whereas for this liquefiable sand layer, what we have chosen is that we have chosen a brine model to take into account the degradation of shear strength and the cyclic shear strength that is generated during liquefaction. Okay, so I have taken this brine model for modeling this top layer, and the pile element was modeled a two-noded straight element with 6 degrees of freedom per node, that is 3 translation in the XYZ and 3 rotation in the XYZ axis. Okay, so I have in this case I have done a three-dimensional problem. Yes, and this is the pile property, the soil property, and since the pile and the soil are two different materials, what we have to do is that we have to use a stiffness. Okay, that is the shear soil pile interface property as given by this particular experiment, this particular formulas, which was taken by Timoshenko and Goodyear, their research 2002. Yeah. Now, the same thing which I have done over here, then how we have simulated liquefaction, that is dynamic liquefaction analysis conducted after assigning a liquefaction model by brine to the Nevada sand layer and with model parameter which is a function of the relative density of the soil. And in fact, there is an inbuilt function called the Finn model which is capable of incorporating the liquefaction model of brine into this Moore-Kula plasticity model. That's what we have. Now, we have done the theoretical, the FEM-based analysis. Then we did the numerical modeling in flat 3D using FDM, and this particular graph, the blue line represents the Tarek-Upton's graph, that is from the dynamic centrifuge test results. And we have seen that the results, both in terms of maximum bending moment and also the maximum pile deflection, shows a similar trend. That is, the values are very close to each other and within around 10%, because that is the maximum generally we put variation that can be allowed in any geomechanics. So we can see that the results are quite close with each other. Now, what we have done is that we have studied the variation of different factors. Firstly, the depth of the liquefiable soil layer. That is, we have considered the problem statement. If you recall the problem statement over here, as we have shown here in this particular case, yes, this maybe in this is much simpler. Here is a liquefiable sand layer, this is a non-liquefiable clay layer. Now what we have done is that we have added the thickness of this liquefiable sand layer for total length of the pile. That is, firstly, if so this is 10 meters, top 2 meters is liquefiable, remaining 8 meters is non-liquefiable. Or in some case, the entire soil is non-liquefiable, and in other case, the entire soil is liquefiable. So in this way, we have done some parametric variations, which is further given in this particular slide. That is, L liquefiable by L represents total length of the pile from point 2 to 1. It is seen from this figure that for both deflection and bending moment, as I increase the L liquefiable by L ratio from zero point 0.2 to zero point 0.6, the pilot deflection is keeping on increasing, and so is the bending moment. Once it rises, however, from zero point 0.6 it rises to zero point 0.8, then the deflection is reduced, while at L liquefiable L ratio at 1, the deflection at the pilot is again reduced accordingly. Why this is similarly, the same thing is observed for the bending moment. Also, we have seen that the maximum bending moment occurs at the interface of the liquefiable and non-liquefiable soil layer. And also, when L liquefiable by L ratio is close to approximately 0.6, the maximum bending moment and hence the maximum deflection will be observed. And I have used for this particular study 4 different input ground motions, that is Kobe, Loma Gilroy, Sikkim, and the Bhuj motion, and it is seen that maximum bending moment around 490 kN is observed for Sikkim earthquake motion when L liquefiable by L ratio is 0.6. However, when it reaches to 1, it reduces to 220 kN/m. This is an observed from the present study. Similarly, we have considered inertial loading, that is, in addition to the kinematic loading, we have considered the effect of vertical loading acting on the pile. It is given by this particular formula, that is, particular expression QV is equals to QH, no Q and no vertical load, 0.25, 0.5 QH, 0.75 QH, and 1 QH. That is, this vertical load is taken as a function of my lateral load. When there is no vertical load acting, it is observed that the maximum inertial component of bending moment and deflection is around 10.2 and 1.2 centimeters. When it rises to 0.5 QH, this again increases, and from this both deflection and bending moment increases. Now, from this we can conclude that the kinematic loading has significant influence on pile response when compared to smaller magnitude of inertial loading. However, pile bending moment and pile deflection is considerably increased in liquefying soil under inertial loading. When this is because of the bending buckling interaction. So the presence of vertical load is very important in any analysis of pile in a liquefiable soil mass. Next is, I have done a comparison between this liquefiable and non-liquefiable condition. It is seen that in case of a liquefiable soil, the maximum bending moment due to Kobe motion is 1638 kN/m, whereas for non-liquefiable condition is 590 kN/m, and hence an amplification factor, that is the ratio of bending moment in liquefiable soil under similar loading conditions to that in non-liquefiable soil, that is given by 2.8 amplification factor. Similarly, for Loma Gilroy, Bhuj, and Sikkim, this amplification factor is 1.7, 4, and 4.2. Both deflection and bending moment has been amplified. Now the question arises that why Kobe motion, which is having a higher PGA at the or a higher MH, the ground level acceleration, bed level acceleration, is showing a lesser amount of amplification as compared to Kobe, as compared to Bhuj and Sikkim motion. This is because if we see the time history of Kobe motion is having less number of load reversals as compared to Bhuj and Sikkim motions. Since for Bhuj and Sikkim, load reversals are much higher as compared to Kobe, so the amount of amplification is also much higher. As a result, the destruction due to these earthquakes were much higher as compared to the Kobe earthquake. Okay, so we can conclude from this is that the time duration and frequency content of an earthquake motion is all plays a much vital role as compared to the bedrock level acceleration of any earthquake motion in determining, in analyzing any in analyzing any geotechnical earthquake windshield related problem. This is the same thing that we have done over here, where we can see that is the amplification factor due to kinematic loading and combined loading, for deflection, and also for the bending moment. Similarly, we have also obtained P delta curve, that is maximum bending moment and deflection due to various loading conditions, that is only for kinematic loading, that is when we have no vertical load, and also when we are having vertical load as given by this expression, that is when we are having an vertical load acting, and how this is varying. It is seen that as the amount of vertical load is keeping on increasing, the deflection and also the bending moment will also increase. This represents my kinematic loading conditions, and accordingly the curves for the vertical loading is also obtained for sinking motion and for Geomechanics. Next thing, the influence of liquefaction and behavior of pile, already which we have studied. Now with respect to different L by D ratios we have done. As we have explained how we have obtained the stiffness liquefaction factor and how eta HN, it is seen that at the top moment at the pile top due to liquefaction is 185 kN per meter, and other non-liquefied condition is around 38 kN per meter, and for an application of 0.5. Similarly for both thickening it is 7.8 and 7.5 respectively. Okay, as we can see for this liquefiable and non-liquefiable. Yes, now this was one of the major, I would say, major what do I say? Outcome of this study is that we could compare our results with JRA. JRA represents the Japanese Road Association coding. Okay, in determining the pile response. What JRA does is that JRA gives the mechanism of analyzing pile response by considering lateral load only at the pile head. Whereas in our study, we have considered the pile load at different depths around the pile length. That is, the lateral load at various depths along the pile length. So, a depth-wise variation of lateral load was considered in the present study, which JRA does not take into considerations. So that's why we can see that in case of present study, we have seen the bending moment, normalized moment is increased by around 21%, and the pile head displacement is increased by 23% for a given loading conditions. So we can say our results give more accurate and practically feasible solutions. Okay. Now the observation we have seen that the maximum displacement and this bending moment is observed when the pile is embedded in liquefiable soil, and thickness of the liquefiable soil is 65% close to of the total pile length. This is because the soil around the pile has already liquefied, and any further increase in the load will not cause any increase in displacement of the pile foundation because already the soil has failed. Okay. Next, maximum bending moment occurs when thickness of the liquefiable soil layer is at the interface of the liquefiable and non-liquefiable soil layer, and when depth of the soil layer is around 60% of total pile length. In case of sinking motion, the amplification factor of deflection and bending moment is much higher as compared to Kobe motions. For smaller magnitude of inertial loading, pile response is significantly affected by kinematic loading. However, as we increase inertial loading, then the inertial loading takes into account, it has a major predominance over pile bending moment and deflection. Also, we have seen that liquefaction potential increases with increase in magnitude of earthquake, but reduces with depth below the ground surface because of the increase in the overburden pressure. So, these are some of the references which you can see. Whatever work I presented in this pile foundations, then these are the references from that. Some papers arising from my PhD work, and as a single author which I have done in IIT Roorkee. Okay. So you can get all these references in details, the entire methodology, the sequential structures, and all those things in these particular publications. Okay. Coming to the next part of the work, that is pseudostatic analysis of sheet pile wall under surcharge loading conditions. The next topic that has been done with this numerical modeling. And for this work, I want to acknowledge my present PhD research scholar, Mr. Akshay Pratap. Now, what are sheet pile walls? Sheet pile walls have a wide application in the field of geotechnical engineering and used as an earth and water retaining structure. Actually, these are all temporary structures. It prevents the material from sliding, and it provides high resistance to the driving stresses. Generally, they are flexible in nature and constructed using thin steel or thin concrete panels or wood. Similarly, like a pile foundation, in case if you are doing any earthquake prone area, Then it is affected by the input ground motion, the site response, external loading, which have a considerable impact on the behavior of the sheet pile in an earthquake prone area. Now I come to the problem statement that I have considered in this present study and what are the different assumptions. Remember, any geotechnical engineering problem that we solve, not only geotechnical engineering, any problem in civil engineering solved that is based on certain assumptions. And so this is the assumption that we have taken, that this A, B, C that represents a sheet pile wall. This sheet pile wall is subjected to a surcharge loading of magnitude small q, and this surcharge is located at different distances from the top of the wall. That is, it is located over here, and gradually this infinite surcharge is moved at different distances, which is given by lambda into h by d, h plus d1, where now lambda is the normalizing distance factor. Okay, lambda is called normalizing distance factor, and at different distances from the top of the sheet pile wall, the surcharge is added. Now, from the basic principles of soil mechanics, what we know, if this is the backfill soil over here, and this point, this line that represents my dredge level, okay, then what do we see? And if H represents the excavated height of the wall, and capital D, or rather in this case D1 plus D2, that represents my embedded depth, then what is happening? This backfill soil is giving pressure on the wall. Now this sheet pile wall will be rotating about a point O. Remember, in this case I have considered a cantilever sheet pile wall. Okay. This sheet pile wall is rotating about a point O. Now, if it rotates about this point O, then what happens? In this particular zone 1, this sheet pile is moving away from the backfill soil. So, this represents an active condition. Whereas between this point B and point O, the sheet pile is moving towards the soil. So, it is in a passive state. Come to that point O, rather below the point O. In this zone 3, wall is moving away from the point O. So again, this represents an active conditions, whereas this wall is moving towards the soil in zone 4, and that represents my passive condition. So basically, to speaking, whatever is the condition above the point of rotation O, below it is the condition is simply reversed. Okay, this is something that we should take into account. This particular method, based on limit equilibrium approach for the design of cantilever sheet pile wall, is based on the following assumptions. The wall soil system is in a plane strain problem conditions. The soil is homogeneous, questionless, and dry. The surcharge is situated at a distance from the sheet pile wall and is uniformly distributed on the ground surface. It's an infinite surcharge. The soil wall interface has a rigid plastic behavior. The cantilever sheet pile wall consists rotation about a point O, which is the pivot point, and we have assumed the linear displacement. That is, the active and the passive earth pressure undergo full mobilization. Okay, that is what we have assumed, that is, both active and passive earth pressure undergoes a full mobilization. And we have considered a pseudo-static approach, that is, the seismic force are assumed to be constant throughout the mass of the system and are directed in the horizontal and the vertical directions only. That is what I have assumed in the present state. Now, for analyzing this type of problem, what we have to do? The first thing is we have to draw the typical earth pressure diagram. That's what we should remember that. And this is the earth pressure diagram for this condition. This represents for the soil, and this represents for the surcharge loading. Okay, now this is the point of rotation. So what we have seen over here, about the point of rotation, we're having active condition over here, passive over here. So Ka1 gamma 1 gamma into H plus D1 and Kp1 gamma D1. Below the point of rotation, it is Ka2 gamma D1 on the top and Ka2 gamma D1 plus D2 on the bottom over here. Similarly, on this side, it is Kp2 gamma H plus D1 plus Kp2 into Q, and bottom Kp2 gamma H plus D plus Kp2 into. This represents the direction of my PP2, PA2, PP1 and PA1. That is the direction in which the active earth pressure and the passive earth pressure acting. It is inclined. Why? Because we have considered the soil wall friction angle or delta over here. So basically, a Rankine's analysis cannot be done. Okay. And this particular figure, this represents separately I have drawn for the surcharge in this zone 1. Okay. So what we have done is that influence of external loading is considered by extending the Coulomb-based theory, thereby incorporating the soil shear strain parameters to calculate the increase in horizontal stress along the depth of the cantilever sheet pile wall because of the surcharge. And this represents the force polygon for this particular one, that is for this particular zone 1. Why? Because we have considered the failure plane to be passing through this particular zone. Okay. So, and this represents total diagram, that is the PA acting delta P1. Epsilon C represents the angle which the failure envelope makes with the horizontal, and this represents the horizontal earthquake force and the vertical earthquake force over here. That is Kh into W, Kf into W, that is my horizontal and vertical pseudostatic earthquake forces that we have considered, and this represents my force polygon. Now, the same aspect I have done in flat 2D by considering a numerical modeling. What you have done, numerical, why you have chosen flat 3D? Because it's essentially a plane strain problem. So using a flat 3D does not make any sense. So we have resorted to flat 2D. Now, numerical modeling of a cantilever sheet pile wall with surcharge under pseudostatic condition is carried out in two-dimensional plane using flat 2D. We have assumed the soil to be fully dry and saturated above and below the water table respectively. The excavation is done in 3 steps. Firstly, we have installed a sheet pile wall, then we have dewatered and accordingly excavated. The excavation is carried in 2 levels and the same construction sequence has been. What is the boundary conditions? The movement of vertical boundaries are allowed in the vertical directions and restrained in the horizontal directions. Further, the movement of the bottom boundary, that is the bottom, is restrained against movement in both horizontal and vertical. The water table is assumed at 2 meters below the ground surface, and the soil wall interface angles have been represented by delta, normal stiffness, and the shear stiffness respectively. Okay. Now, this is basically the numerical model that has been chosen in the present study in flat 2D, which is essentially a finite difference-based computer program. The size of the domain and density of the mesh influences any numerical analysis and are determined as per the convergence. Remember, this is a very important thing. Is that domain size, total size of the soil block that we have considered, then the type of mesh, that is whether we are going for a coarse mesh, a fine or a very fine mesh. Okay, so all those things do have a very important role to play, and this has been done by carrying out the convergence study. What is a convergence study? Okay, now what we have done is that we have taken arbitrarily so unit weight of a soil friction angle, interface friction angle, and the sheet pile wall having an embedded depth of 4 meters, excavated height of 4 meters, and a flexural rigidity given by this particular expression. Next, what we have done is that we have determined what is the magnitude of bending moment for different width of the backfill. That is, for this case, we are determining what is the width of the backfill. That is our main target. You have to know that. So what we have to do is that for that we have to assume the other 2 parameters. So what I have taken is that I have taken a 0.5 meter by 0.5 meter mesh size, and I have taken a depth below the dredge level as 5 into H plus that I have considered. And with this, I have run the analysis and obtained a bending moment. What we see that it is seen that the width of the backfill soil 6 into H plus D, 8 into H plus D, and 10 into H plus D gives approximately the same bending moment values. That is, for these 3 cases, the magnitude of bending moment is almost observed to be same. That shows that for the given depth and the mesh size, if we keep on increasing the width beyond a certain dimensions, there is no effect on the physical parameters. Okay, this is one. Next is we have determined the depth. So what we have done, we have assumed different depth, that is 2 into H plus D, 4, 5, and 6 into H plus D, and having a constant mesh size of 0.5 meter by 0.5 meters, and the backfill distance of 8 into H plus D that we have considered. We have seen that for 4, 5, and 6 H plus D depths, the bending moment along the depth and above it almost remains the same, and it's slightly below. That is, for these three cases, the same variation bending moment allowed the depth above the point of maximum and differ slightly below. That is, almost the same results are observed. So we are, from this case, we can fix the depth. Next thing that comes, what is the mesh size? Okay, so bending moment versus depth curves for different mesh size with approximate size of the domain, because the backfill distance and the dredge level distance already I have fixed, that is 8 into h plus d and 5 into h plus d from my convergence study. So I have taken 5 different mesh size from extra course and it is going on final. What we have seen is that for 0.33 meter by 0.33 meter, 0.25 by 0.25 and 0.2 meter by 0.2 meter, it is almost giving the same value of my bending moment at the particular depth. Clear? So what we have done? Finally, we have selected a size of domain having backfill distance 8 into h plus d, depth below the dredge level 5 into h plus d, and the mesh size of 0.25 meter by 0.25 meter. If you see in this particular figure, that is what we have done. This is how we have arrived at the dimension of the loop. This is very important so that the boundary effect is avoided. And arbitrarily, we cannot choose any domain, because if we keep on increasing the domain, and obviously if we keep on making it a very, very fine mesh, my computational time is also going to increase. That is also an important thing. Do not make it too coarse, because in that case, you will be getting an approximate result. And also in some condition, it will happen that since in fact we perform a Lagrangian analysis, that is, at every step, the grids are modified and analysis is done with respect to that particular new grid. That is the Lagrangian analysis that we are following in this flat software. So what is happening is that if we are making a very coarse mesh, and if under the subject, it is subject to a various external loading, it might happen that the mesh will get deformed or distorted and analysis will be arbitrarily stopping. It will show irregular geometry. So that's why we have to generally have to go for a final mesh. One, it will give accurate results, and the problem that is encountered with this bad geometry, that can be avoided. But thing is that also one more thing, that is, here we have seen that for both 0.25 and 0.2 we are almost getting the same result. Then why don't we went for 0.2? We could have gone for 0.2, no problem, but in that case the computational time again has increased. So we resorted to 0.25 and 0.25. Why? Because we have seen that 0.33, this three particular 0.33 and 0.25 and 0.2 almost gives the same values of bending moment. So we have taken the center one, that is 0.25 meter by 0.25 meter. I hope it is clear. Now, any numerical work, as I have told in the case of pile foundation also, that needs to be validated. So what we have done here, we have validated our work with the dynamic centrifuge test results of Madabushi and Zeng that was carried out in Cambridge University in 2006. This is the various soil properties and the pile properties that we have done, and we have seen that the bending moment distribution of the present result with that of numerical result and the experimental result is showing a good agreement, and there is certain discrepancy, and it may occur. Why? Because the result, this may be due to implementation of centrifuge test and also properties assumed in the numerical modeling. Because in research papers, all the properties sometimes might not be given, so from standard references, we sometimes have to choose the properties. So we can see that the small minute variation of result is there, which is very acceptable. Excuse me.
Yes, sir.
Yeah, okay, no thanks.
Okay.
Similarly, we have also validated our results with the experimental results of Chawla et al., who have performed the laboratory experiment in a steel tank of length 1.2 meter and depth of 0.5 meters as the entire dimension of the domain, that is 1.2 meter by 0.5 meter steel tank, that is the soil domain they have considered, and this is the sheet pile property, and total length of the sheet pile was 5 centimeter. All those things they have done. Okay, and what we have done is that we have computed the total displacement. Okay, it is seen that there is less difference at deep displacement for excavation of 550 meter, 100 millimeter, and high difference at excavation, that is depth of cutting around 200 millimeter. Okay, so the chances of errors were quite low in this case. Now we have come to the, after the validation of the work is done, now we have come to the present study where we have done a pseudostatic analysis. What we have done? We have investigated the response of the cantilever sheet pile wall under the influence of surcharge loading and at varying distances from the top, and we have presented the results in terms of normalized parameters. As much as possible, we should give our result in terms of normalized parameters. Like bending moment can be normalized with m by gamma h cube. Earth pressure can be normalized as sigma by gamma h. Why? Because if you're normalizing it, obviously the influence of various parameters are automatically taken into consideration. That is, the problem with units that might really happen can be avoided. Okay, so that's why in most design problems or design charts that we have, the results are presented in terms of non-dimensional parameters. The depth is normalized with total length of the sheet pile wall, that is Z by D, and infinite uniform surcharge is represented as Q by gamma H, or it is by capital Q. Okay, and the height of the excavation was assumed as 4 meters, whereas the embedded depths were taken as 4, 6, 8, and 10 meters. That is what we have assumed in the present study. This is the angle of internal friction, that is 30, 34, 39, signifying loose sand, medium sand, and dense sand. And we have varied the distance of the uniform surcharge from various distance to the top of the wall. That is from 0 meter that presents the surcharge loading is placed directly on the wall top, and the 12 meter means far away from the top. Okay, this is what we have done. Now we have studied what is the influence of the magnitude of surcharge on this D by H ratios. First case, lambda is equals to 0, and next one for lambda is equals to 0.1, 0.2, like this, where lambda represents the depth factor, that is, I mean, the distance factor, distance from the surcharge loading from the sheet pile wall. Okay. Now, if I increase the magnitude of the infinite uniform surcharge from 0 to 100 kPa, the D by H ratio is increases in this particular manner. Okay, with respect to the previous value when lambda is equal to 0. The rate of increase of D by H ratio decreases when the magnitude of infinite uniform surcharge is keeping on. Okay. Next is for different distances of lambda varying from 0.1 to 0.5, the D by H ratio decreases from 0.66 to 0.49 respectively. What does it mean? That means as the value of lambda, that is as the sheet pile wall, as the surcharge is moving away from the sheet pile wall, then what is happening? Its effect on the sheet pile wall is being reduced. So correspondingly, my D by H ratio is reducing. And we know that in case of a cantilever sheet pile wall, the main stability comes from the passive resistance below the point of below the dredge level. That is, it imbibes its main stability from the sufficient shear strength. So that's why it does not require that much of embedment. So that is what is given over here. The rate of decrease of D by H ratio is almost constant for low magnitude of infinite surcharge and increases at higher magnitude of surcharge. Okay. So that is what we have done over here. An increase in magnitude of infinite surcharge requires more depth of penetration to get stability, as cantilever sheet pile walls get stability from the passive fault resistance below the dredge level. As the distance of surcharge increases, the influence on the cantilever wall is reduced. Now, when seismic force are considered or applied on the cantilever sheet pile wall, the variation of D by H ratio is the same. However, as this increases, the magnitude of KH increases from 0 to 0.5, more penetration depth is required to generate sufficient amount of passive pressure below dredge level. And it is seen that for D by H, for Q 50 kPa and lambda is equals to 0.2, my D by H ratio increases to 1.6 when my KH value becomes equals to 0. Because to get more stability, we require more embedment. Next is influence of D by H on D1 by D2. Now, what is the small d1? If you recall the figure which I have shown over here of the initial problem statement, yes, this one, d1 represents the distance of this point of rotation from the wedge level. Now, below the point of rotation, that is below this particular point 2, this zone 4, this represents my passive zone. Okay. That is the most stability is being obtained from the passive resistance in this particular zone. So if my point of rotation moves upwards, then the passive resistance will be much higher as compared to the condition if this point O moves downwards. Clear? That means if more is the load, external loading that is coming, on this case, my point of rotation is supposed to move up so that we get maximum strength from this particular passive resistance is developed. Now, if I come to the study that we have done over here, yes, the d1 by d ratio for corresponding d by h is this are 0.91, 0.9. So, from whatever the d by h we have obtained in the previous case, the d1 by d we have studying over here. We seen that d1 by d decreases for an increase in d by h from 0.42 to 0.98 is 2%, while for higher d by h, it decreases about 0.3%. That is, the location of the pivot point is away from the toe where the required penetration depth is quite large. Okay. Now, does that mean that it will keep on moving upwards? No. After a certain point, this d1 value will be the d1 by d ratio will be remaining constant. That means by d1 will never be touching the dredge level. It will be located somewhere below the dredge level. Okay. The results are on the same result we have compared with Mathabhushan Chandrasekharan and the centrifuge test, and also we observed that the results that follow the similar trend. That is, the prediction of location of pivot point determined through the proposed model is almost similar to location of pivot point determined using the minimization moment ratio that was done by Chandrasekharan and Mathabhushan. Next is, what is the magnitude of distance surcharge on the d1 by d? Okay. So for Q equals to 100 kPa, we have seen that d1 by d is about 0.9% when uniform surcharge is shifted from 0 lambda equals to lambda equals to 0.5. And when the magnitude of surcharge increases from 0 kPa to 100 kPa for lambda equals to 0, then the increases the location of pivot point by 3.1%. That is, it can be seen that increase in the magnitude of infinite uniform surcharge, the location of the pivot point moves upwards and away from the toe of the cantilever sheet pipe. Okay, that is, it is giving more strength by increasing the passive resistance. This is due to sufficient presence of passive earth pressure below the dredge level to stabilize the structure. The increase in distance of placement of uniform surcharge locates the pivot point towards the toe of the cantilever sheet pile 1 because obviously its effect is being gradually reduced. Similarly, for delta by phi ratio, that is delta we have varied from 5 by 3 to 2.5 by 3, and we have seen that as kh increases from 0 to 0.5, the d by h increases from 0.42 to 0.21 for delta by phi is equal to 6.67, and when surcharge increases to from 20 kPa, again the d by h ratio will increase to 1.35 for a given delta by phi ratio. Okay, so with the increase in seismic force, there is an increase in d by h ratio to get stability from passive earth pressure developed below the dredge level. And increasing the soil wall frictional angle will obviously decrease the requirement of passive earth pressure, resulting in a lesser d by h ratio because it will be imbibing more strength to the soil type. That is, when no surcharge load is acting, okay, the penetration depth for different magnitudes of kh is this, while there is q equals 20 kPa and lambda is equals to 0.2, the d by h ratio increases to 24.6% in dense sand. The reduction in friction angle increases the d by h due to less soil resistance that is being provided by the soil particles. Moreover, as we change from the loose sand to dense sand, requirement of penetration depth will decrease as the mobilization of earth pressure will decrease. At lower value of seismic coefficient, there is less difference in the penetration requirement, but as the inertia force will increase, more difference will be required and the higher penetration depth will be observed. Okay, now we go to the variation of bending moment with depth. Okay, that is for different magnitudes of earthquake from kh equals to 0 to 0.15. It is seen that the normalized bending moment increases, okay, around 279%, as we can see from this particular figure. As the horizontal seismic acceleration coefficient is increased, the maximum normalized bending moment also increases, following the same pattern but the location of the maximum bending moment slides down the depth to account for the increase of the seismic inertia forces. Similarly, the vertical inertia force also plays a very important effect, and it destabilizes the sheet pile wall if applied vertical. Generally, remember that for vertical seismic inertia force, there can be two directions, either in the upward direction or in the downward directions. So, and the detrimental will be one in which the stability of the sheet pile wall will be reduced. And it is seen that if it is applied in the vertically upward direction, it renders the structure to certain more bending moment. It has become unstable. Okay, here. Next is on the earth pressure. So horizontal earth pressure are developed around the sheet pile wall during construction process due to movement of the soil mass. Generally, active earth pressures are fully developed due to wall movement of 0.1% to 0.4%, whereas 5%, 20% wall movement necessary for full mobilization of passive earth pressure. That's why active is always fully mobilized, whereas passive is partially mobilized. Remember that. It's an assumption that we follow that both active and passive are mobilized completely. However, it's not always correct. It's an assumption that we usually do. So, more realistic results will be observed when we go for a partial mobilization of the passive earth pressure. The percentage variation depends on the type of wall movement and soil present in the backfill. Due to less movement of requirement of movement for active earth pressure to be developed, the soil behind the sheet pile wall is an active living condition up to a certain depth below the dredge level, whereas in front of the wall immediately below the dredge level, passive earth pressure is fully mobilized. Okay. Now coming to this one, it shows horizontal earth pressure versus strength, and it is from both active side and also the passive side. It is seen that as we increase KH from 0 to 0.2, the active earth pressure in the backfill increases, and this increase in the active earth pressure causes the mobilization of the passive earth resistance to a larger depth to satisfy more equilibrium in front of the wall. The inertia force in the form of seismic condition redistributes the earth pressure, causing the increase in bending moment of the sheet pile wall. Similarly, as we increase the vertical seismic acceleration coefficient, that is as Kb increases, the more mobilization of passive earth resistance takes place, resulting in increase in the depth of full mobilization. The influence of horizontal seismic acceleration coefficient on analysis of sheet pile will observe more than the vertical seismic acceleration coefficient because gravity can counteract the vertical acceleration coefficient, but in horizontal directions, more unbalanced inertia force is generated. That's why KH plays a very significant role as compared to KB in this particular studies. Next, with the magnitude of the normalized surcharge loading, presence of uniform surcharge load at top of the wall affects the bending moment and earth pressure by mobilizing the earth pressures. Cantilever sheet pile when loaded with uniform surcharge at the top of the wall with different normalized depth shows the increase in normalized bending moment with increase in surcharge loading. It is as my surcharge loading is increased, this bending moment is keeping on increasing, and almost 118.7% is increased when we have around 100 kP of surcharge load. Influence of magnitude of surcharge load. For all magnitudes of uniform surcharge, the normalized bending moment increases with increase in horizontal seismic acceleration coefficient. However, the rate of increase in normalized bending moment is dropped when seismic coefficient is there. Will increase in magnitude of seismic coefficient at a high magnitude of surcharge loading. This is because of the high inertia curve. It almost is becoming constant. Similarly, for magnitude of surcharge loading, the normalized earth pressure from no surcharge conditions to deferred magnitude of surcharge loading, lateral earth pressure around the wall will increase, thus increasing the depth of full mobilization of passive earth pressure below the dredge level. Okay. The increase in earth pressure increases the bending moment to satisfy the moment equilibrium conditions. It is also observed that the pattern of the earth pressure is similar for different magnitudes of uniform surcharge. It is almost following the same trend. Next, the existence influence of the position of uniform surcharge. Now, the position of surcharge at a distance from the top of the wall is a normal condition and can occur at any time or point during the life of a structure. Although these structures apply load on a bounded surface, but in the present study, we assume that it is an infinite uniform surcharge loading and it is placed at different distance from 1 meter, 2, 3, 4, 5, 6, 8 meter and 12 meter respectively. And This is defined by a normalized parameter from the lambda, that is ratio of distance of surcharge from the top of the wall to the height of excavation. That is the ratio is given by the lambda. So lambda is varied from 0 to 3 if we normalize it, and it is seen that for kh equals to 0.1 and kv equals to 0, the as lambda increases from 0 to 3, the normalized maximum bending moment reduces by around 32% between the position of surcharge top of the wall and far away. Similarly, for different values of kh, if the distance of the uniform surcharge increases from the top of the wall, the normalized maximum bending moment decreases, and it is almost constant beyond lambda equals to 1. That is, beyond the particular distance factor lambda, wherever we place our surcharge loading, it is not going to have any influence on the bending moment. The constant value of bending moment, normalized bending moment, is approximately the same which occurs when there is no surcharge placed for all values of t. That is, whatever is the max bending moment value I get, it is almost similar to a no surcharge loading condition. Similarly, for uniform surcharge of 0.68 and kh as 0.05 kV equals to 0, the normalized maximum bending moment varies in this particular manner. It reduces as my lambda increases from 0 to 2 respectively, and decrement of 46% is observed as the position of the surcharge changes from the top of the wall to far away from the wall. Same thing is observed for other magnitude of surcharge. Now, influence the position of the surcharge loading for different magnitude of surcharge load. When the uniform surcharge is placed on the top of the wall and up to say 0.75, lambda is equals to 0.75, normalized maximum bending moment increases with increase in magnitude of uniform surcharge. However, beyond that, no difference is observed in the bending moment. The rate of increase of normalized maximum bending moment is maximum when the surcharge is on the top of the wall, and beyond that, no effect will be observed. This rate of increase is reducing. The same thing is done over here with respect to the normalized earth pressure. We have seen that maximum lateral earth pressure around the cantilever wall are obtained when the surcharge is at the top of the wall, and as one moves away, lateral earth pressure will be decreasing. Similarly, for the angle of internal friction, that is for lower values of angle of internal friction, the maximum bending moment will be much higher as compared to the higher value of the bending moment because of the more passive resistance being developed. Okay, the next is as the density increases for a particular seismic acceleration coefficient, that is under seismic condition, the normalized maximum bending moment reduced from 30 degrees to 39 degrees of 5 values. For the variation of earth pressure, for this condition of loading, the earth pressure increase of 30 degree gets mobilized to a greater depth as compared to that. The greater mobilization activity less resistance offered by the soil owing to a lower angle of internal friction. Also, the active earth pressure for 30 degrees, if I compare with 39 degrees, is thus creating more earth thrust and hence more bending moment. Also, the active earth pressure for 30 degrees is more due to less angle of internal friction. Next is effect of the embedment depth. Now we have taken 4 different embedment depth, and by D by H ratio it comes to 1, 1.52 and 2.5. The cantilever sheet pile wall generally derives its stability from the passive resistance developed below the wedge level. As the kh value increases, the maximum normalized bending moment will also increase for different normalized depths. The normalized bending moment increases in this particular manner for the given loading condition in a dense sand. It is because as the embedment depth will increase, the sheet pile wall will become more stable and will sustain more load and hence more bending moment. Similarly, it is also observed that if the embedded depth is small, the structure cannot sustain high seismic load as seen for this case, as we have seen that for dH by H is equal to 1, it's the maximum seismic load it can sustain. Okay, similarly, for the variation of earth pressure, we show that the variation of normalized net earth pressure along the normalized jet for various normalized ratios D by H shows that development of plastic zone below the dredge level. What is plastic zone? The plastic zone is defined as that zone up to which full mobilization of passive earth resistance below the dredge level will be existing. Okay, it is that particular zone up to which mobilization of passive earth pressure, that is full mobilization of passive earth pressure below the dredge level will be existing. As the normalized embedded depth increases, the development of plastic zone and hence net passive earth pressure at bottom of the wall will be decreasing. It has also been clear in this particular figure. That is that for the normalized depth of the plastic zone and normalized net passive pressure, we have seen that as the embedment depth will increase, that is the development of plastic zone below base level and net earth pressure at the top of the wall decreases. This decrement is development of plastic zone occurs below the base level and net earth pressure at the top of the wall occurs due to significant reduction in horizontal displacement of sheet pile. A similar pattern was also observed by Conto et al. For their new theoretical study for cantilever sheet pile under no such conditions. That means that as my D by H ratio is increasing, the depth of the plastic zone is keeping on increasing. So these are the major conclusions which I've already have discussed in the course of work. Again, I'm not repeating it. And these are the publications that has been coming out from this particular work. So in ASC, IJOG, and Arab of Geosciences, and we're having the National Academy of Sciences and also our Indian Geotechnical Journal. So this sums up the second part of the numerical modeling. Now I go to the third portion on which the work is now, it's actually started. That is the response of caissons, that is well foundation to seismic loadings. And acknowledgement goes to my present PhD research scholar, Mr. Mohit Kumar. And caisson study is one of the unexplored areas in geotechnical engineering. Not significant amount of work has been done in this particular field. Okay, now what are caisson foundations? And caissons or well foundations are usually enormous substructures that resist a variety of load combinations, and this transfers into the soil below. So they are mostly suited to be used as a bridge pier over a bridge and a pier foundation over a bridge or over a water body. They are very important foundation systems and they support the lifeline of structures. And since they support bridge and other lifeline of structures, a failure of a well foundation can be very, very catastrophic. That is, it can lead to its failure. The large diameter and depth of a caisson provide sufficient stiffness because usually caissons are rigid structures. So, because of the large diameters and hence sufficient stiffness is there to resist the load transmitted by these wires. Under the action of lateral load and externally applied movement, the soil reaction, horizontal and vertical shear traction and bending stresses are developed. And this caisson, what happens? It will tilt about a point above the base of the caisson. Why? Because there's mostly rigid structures and they will be tilting about a point above the base, and lateral soil distribution is in accordance with the tilt of the caisson. However way the caisson is tilting, the soil distribution or the soil pressure distribution will be accordingly with that. So what is the objective of the study? In this particular study, we have done is that we have modeled a caisson foundation in a typical layered soil with pore water pressure passing through it in Abacus computer program. It's a finite element based computer program. A series of numerical analysis for different parameters like the wall friction angle, the seismic acceleration coefficient, vertical and lateral load have been performed to investigate the influence of the behavior of the caisson. The results of this analysis have been further used to obtain interaction diagram. What is this? In VQM, V represents the vertical load, Q represents my lateral load, and M represents the moment. The results of this analysis have been further used to obtain interaction diagrams in the VQM space, indicating the load combination for positive values of shear force, bending moment, and vertical load, lateral load, and bending moment that is causing the failure. That is, we have obtained the critical combinations of VQM that will indicate failure of the caissons. This is what we have done. And how this interaction diagram have been developed, we will explain more in the later part of the work. So an extensive numerical study has been performed by applying a large combination of vertical and lateral loads. For the development of interaction diagram, the load combination which gives a negative magnitude of minimum base pressure has been chosen in the present study. And the curves are plotted in VQM space for different values of delta, KH, and K. If we look at this statement, the load combination which gives maximum negative value of minimum base pressure. In generally, for any design of well foundation of the caissons, we have to consider two different things. One, what is the minimum grip length? Secondly, what is the maximum or minimum base pressure? and this should be below the permissible limits. Okay. Maximum base pressure will be positive and it should be less than what is allowed from the codal calculations. Now, minimum base pressure. We know that soil is weak in tension. Okay, it cannot take any tension load. And negative pressure means always it is a tension condition. So the moment this negative base pressure will be turning out to be negative, that is minimum base pressure is turning out to be negative, that means soil has entered into a tension zone, it cannot take any further load. So that particular combination in which this minimum base pressure will turning out to be negative, that will be considered as the critical situation for development of this interaction curves. Okay, so this is the model that I have considered. This represents the caisson. A is the excavated height. D represents my excavated depth, embedded depth. B is the vertical load. Q is the lateral load. A moment is generated at this depth is called the cover depth or the cover level. Moment is generated at the cover level. We are having a sandwich soil by the top sand layer, followed by a saturated clay layer, which is followed by a bottom sand layer, and this is resting on some impermeable soil strata. Okay, this is what we have considered. This represents the water table, and we have allowed a flow of water through this soil mass. Diameter of the caisson is 1.5 meter by 1.5 meter. The embedment depth is 2.25 meter. It is capital D. Sand layer, the top sand layer is 3 meter thick. The bottom sand layer is 4.5 meter thick, and the clay layer is saturated and it is 4.5 meter again. The next is the after doing the convergence study, the soil domain is in 3 dimension. This is kept say equal to 30 meter in the direction of lateral load, that is in this plane, and in this other direction that is perpendicular to it, or in the transverse direction it is kept as 20 meter. Okay, so this is what we have assumed over here. Now, the top and bottom soil layer, how have we modeled? The top and bottom soil layers have been modeled as elastic mode Coulomb plastic model, whereas the clay layer, this one is assumed is modeled as a CAM-K model. Okay, that is what we have taken. And we have assumed 8 noded 3-dimensional porous continuum brick elements for the flow of water through these soil layers, whereas this continuum brick elements have been chosen for the case. This is what we have assumed from abacus. This represents the model in abacus, and this particular figure represents the model with the loading conditions been applied and also with the boundary conditions. What have we done? A fixed boundary is applied at the bottom to simulate rigid impermeable strata, because we have seen that it is resting on a rigid impermeable strata. So fixed boundary is done at the bottom, whereas roller support that provided at the sides boundaries to allow for settlement of the soil, but restrained against lateral movement. So no lateral movement, but allowing settlement. A Lagrangian multiplier method has been used to establish contact between the caisson and the soil. So material nonlinearity, geometric nonlinearity, and contact nonlinearity have been incorporated in the present study. Pore water flow has been allowed, so fluid boundary condition has also been met. Now, again coming to the validation, the numerical modeling has been validated with the experimental results of Sharda 1975, and whatever Dr. Sharda has assumed in his thesis work, the same dimensions of the model have been kept in this numerical study. And what Sharda has done is that Sharda has varied the lateral load from 4 kilonewton to 12 kilonewton and has assumed the lateral soil pressure, observed lateral soil pressure for a vertical load of around 1250 kg. For validation purposes, we have also taken into consideration the same loading, and we have also observed the lateral soil pressure, and a maximum variation around 8.8% was observed, which is within acceptable limits. So this is the property that has been done: sand property, the clay property, and the caisson property that has been considered, and we have varied that loading conditions: the vertical lateral loading, the wall friction angle, and the seismic acceleration coefficients. And using abacus, we have obtained displacement, and then by writing a program in MATLAB, we have determined what is the maximum minimum base pressure, the rotation, point of rotation, the tilt, and the shift, and the lateral soil pressure. This has been observed after writing a program in MATLAB after taking into consideration the abacus analysis results. Okay, now how we determine the ultimate what is the allowable load capacity for the case. The allowable vertical load expression has been given in IS 395/1967 using this expression, where we can see that it is the function of the SPTN value, the diameter of the caisson, or sorry, the depth of foundation of the caisson below the waterless cover level, and also the D, which is the smaller dimension of the well section. In our study, it is equal to 1.5 meter because we have assumed the square caisson. Okay. Now, problem is this particular correlation that has been given by an IS code is almost out of date. It's almost obsolete and no one uses it. So what we have done, we have considered a typical soil element, and we have carried out a numerical analysis of the soil element to determine the stress strain curve of the soil. And the load, that is where the curve changes its slope or changes its sign, at that particular point, we have assumed it took the yield stress, and we have multiplied with the base area of the caisson to determine by the ultimate load, and has been divided by a factor of 63 to obtain the allowable vertical load, which in the present study has come out to be 1600 kilonewtons. Okay, and then we have done the parametric study by varying the vertical load V as VA by 8, VA by 4, in this way till VA, and for each of this vertical load, the lateral load is varied as V by 8, V by 4 till V. So overall, there is 64 combinations of vertical and lateral load. The lateral load actually was applied at an elevation of 2.25 meter, the width of the caisson above the scour level. Okay, and hence the applied lateral load and moment were always proportional, like this expression, that is 3.375. That is I would say the excavated height, or this, as we have seen in this particular figure, this H comes out to be 3.375 meters, and this D comes out to be 2.25 meters. Now, for creating the interaction diagram, we have said that we have to determine that combinations of Q by Vn, where the soil pressure, minimum base pressure, is turning out to be negative. Okay. And for development of these interaction diagrams, the vertical load, lateral load, and the moment are normalized with respect to a standard quantities that takes into account the geometry and field conditions, so that these diagrams can be used for all situations. So for this case, what we have used is that we have used the expression as obtained by this IS code to determine what is QA, and that is determined to be 1000 kilonewton. And using the standard value of 1000 kilonewton, we have normalized the vertical load, lateral, and normal moment. Now, what is the justification behind that? Because we have seen that the expression as given by this IS code takes into account the SPTN value, the field strain parameter, and also the dimension of the caisson. And under all circumstances, it might not be possible to carry out the numerical analysis. Also, although numerical analysis gives a more accurate result, still in this case, we have considered 1000 kilonewton as the normalized vertical load. The results obtained from this abacus are used to calculate lateral soil pressure, maximum minimum base pressure, tilt, shift, and point of rotation of the caisson by writing a program using MATLAB. That is how we have done this. Okay. Now let us come to the results and the discussion part, that is the variation of the lateral. First case, lateral soil pressure and with the influence of the lateral load. What we see that the lateral soil pressure is maximum towards the edges over here, and it decreases as one moves from the edge towards the center. Why? This is because of the higher stress concentration that is taking place at the edges. That is, towards the edges, the stress concentration is much higher. And if for a constant vertical load of 800 kilonewton under static conditions, if the work has been done, as Q by V rises or lateral load rises by 25%, the soil pressure increases by 29% at the center and 30% towards the edges. Okay. Why I have said that lateral load rises? Because my V is basically constant. V is 800 kilonewton, so my Q is actually rising. Similarly, if I consider along the depth of the caisson, it is seen, truly speaking, the maximum soil pressure should have been on the top. However, since no overburden pressure is being acted, so we are having the maximum soil pressure at a certain depth below, that is around 0.3 meters below the scour depth. So that is one of given over here. Maximum magnitude lateral soil pressure occurs at a 0.3 meter depth slightly below the scour level for all magnitudes of lateral load. And similarly, if we increase the lateral load, by 25%, the both the this magnitude of lateral soil pressure will increase. Similarly, for different delta values, that is 5 by 2 to 5 by 3 and delta is equals to 5, it is observed that as the lateral soil pressure, as this wall friction angle is increased, lateral soil pressure produced by surrounding soil on caisson reduces. This is because the caisson soil interface with higher magnitude of delta will resist the displacement, thereby producing lower lateral soil pressure along the width and the depth of the. As delta increases from 5 by 2 to 5, the lateral soil pressure along the width of the caisson reduces by around 10.85% respectively, and along the width it is around 13.48% respectively. So both of them will decrease as my delta value will be increasing. This shows the variation with respect to the width of the caisson for and along the depth for different seismic accretion coefficient, that is when kV by kh is equals to 0.5 and along the width and along the depth, and when kh is equals to 0.2 for different kV by kh ratio. What do we see from this study is that kh and kV will be having an effect, and as the value and magnitude of both kh and kV increases, there is an increase in horizontal and vertical seismic coefficient, accretion coefficient. With the increase in magnitude of lateral soil pressure, the for increase in kV by kh ratio is minimal. It is more for increase in magnitude of kh. Why? Because increased seismic horizontal coefficient will cause an increase in displacement of the caissons. So that's why, as the kh value is increasing, the this lateral soil pressure is also increasing. Also, the soil gets compressed under seismic forces. The combination of these two factors leads to greater soil pressure, which is a direct function of the displacement. As we given over this particular statement, this two over here, when V is equals to 400 kilonewton, Q by V is equals to 0.5 and kV by kh is 0.5. When kh increases to 0.3, the lateral soil pressure increases by 35% and 37% along the width and depth of the caisson. However, if we fix kh as 0.2 and if we increase kV by kh ratio to 1, the increment along the width of the caisson is 2.17%, whereas along the depth it's around just 2%. So hardly any effect of kV is observed. The next one is the maximum and minimum base pressure. So we see that at lower magnitude of vertical load, the magnitude of maximum base pressure increases with increasing lateral loading. However, at higher magnitude of vertical load, the maximum base pressure will increase and then it will reduce, because at higher magnitude of lateral load, yielding of soil takes place, causing reduced magnitude of stress owing to strain softening. Because soil has already yielded, it has reached the maximum magnitude, and after that, because of strain softening, it will be resulting reduced magnitude of stresses. The same thing, to recall, was also observed in pile foundation problem. For a 600 km vertical load, as the normalized lateral loads increase from 0.25 0.375, the base pressure increases by 13.26%, whereas from 0.75 to 0.875, that is for the base pressure increases by 2.7% for the strain softening. Okay. Similarly, for a higher magnitude of vertical load, also that is around 12 kilonewton, similar things are also observed. Now coming to the minimum base pressure, it also decreases monotonically for smaller magnitude of vertical load, and post yielding the negative magnitude further decreases. And similarly, it is the same thing. We also observe that the magnitude of vertical load increases, the normalized load required to induce negative base pressure also increases. This increases the higher magnitude of vertical load and causes the caisson to be more stable even at larger magnitude of lateral load. Next thing, if you see this particular figure of this normalized lateral load versus minimum base pressure, we can see that close to Q by V equals to 0.4. This curve, that is for V is equal to 1600 kilonewton, it is crossing the y-axis, and the x-axis, and below that is normalized base pressure is turning out to be negative. That means for a maximum vertical load of 1600 kilonewton, we can say that the minimum base pressure over here will be turning out to be negative when my Q by V ratio becomes 0.4. That is, We can say this Qn by Vn, that comes out to be 0.4, or which in the present study has been considered as 0.45. Okay, this has been done for developing the interaction. Similarly, if we see the Wolfration angle conditions, we have seen that higher the magnitude of delta I explained, the safer is the foundation system since it returns lower magnitude of maximum and minimum base pressure. If we increase the lateral load from 150 kN to 600 kN, as delta will increase from 5 by 2 to 5 by 3, the maximum base pressure decreases by 6.27% and minimum by 5.17%. The foundation system with larger delta dissipates larger share of the applied load through shear stress development along its boundary, resulting in lower bearing pressure surface. This is another part of the work. Actually, this we are on the verge of doing it. That is the load sharing mechanism, or in case of caisson foundations. Again, this is for the different magnitudes of kH and kV. It is seen that for 600 kN vertical load, as my kH increases from 0 to 0.3, the magnitude of maximum base pressure reduces by 5.03%, whereas minimum base pressure increases in negative magnitude by 48, around 50%. It has been observed from the present study. Similarly, for 600 kN vertical load, when Q by V is equals to 0.5 and kH is equals to 0.1, the magnitude of kV by kH increases to 1. The maximum base pressure reduces by 7.1% over here, as you can see this particular figure, whereas minimum base pressure will increases in negative magnitude by around 13%. Okay, as it is clear from this particular graph which we have drawn over here. Next is the seismic acceleration coefficient. Here on the minimum base pressure, it can be observed that soil pressure corresponding to kH is equal to 0.3 does not progress up to a small value of Q by V because of the maximum displacement that has already taken place, and hence the program is aborted because the minimum strength that we have input in the abacus program has already been encountered, and beyond that the program has been aborted. Since the soil is weak in tension, loading combination at which minimum base pressure turns negative as failure load was considered. This load combination normalized with respect to Vn has been used for the development of interaction curve, which we have seen in this particular graph as equals to 7.4. Displacement of the caisson. So as we are increasing the lateral load, say for a particular vertical load, we have seen that the linear nature of the curves has been observed, and it is at covered level. It will be observed that caisson displacement increases with increasing lateral load, and hence a rigid behavior will be seen. Similarly, as we increase the Wolfration angle from delta is equals to 5 by 2 to delta is equals to 5, the magnitude of this lateral displacement reduces. Okay. Similarly, if we increase the horizontal and vertical acceleration coefficient, we causes that caisson displacement increase with increase in magnitude of kH and kV. Okay, the horizontal force have a more significant role to play. For V is equals to 400 kN and Q by P is equals to 0.5. As my kV by kH ratio increases to 0, for a kV by kH ratio is equal to 0, as the kH will increase from 0 to 0.3, my caisson displacement is increasing by around 147%. However, for a particular kH, if I increase my kV by kH ratio from 0 to 1, it is increasing by around 3%. So hardly kV has any role to play in this caisson displacement. Okay. Now coming to another important part of this studies and well foundation is the tilt, shift, and point of rotation. Okay, that's another important part for any study on caisson foundations. For a smaller value of the applied vertical loading, say from vertical load has been varied from 200 to 1600 kilonewtons, and we are observing both tilt and shift characteristics. At higher vertical load magnitude is close to the level vertical load with high. So if my vertical load is increasing, obviously Q is a function of my vertical load. So Q is also increasing. The soil reaches a plastic state and high values of tilt and shift are obtained. For low value of vertical load, that is 200 kilonewton, as the Q by V increases from 0.375 to 0.5, tilt increases by 45% and shift increases by 56%. Whereas for 1600 kN vertical load and for the same increase of lateral load, tilt increases by 52% and shift by 111%. Both tilt and shift increases non-linearly with lateral load at a higher magnitude. Okay, this is what we have seen because as we have clearly shown over here, the soil reaches the plastic state and high value will be observed. Next, if we increase the value of the soil wall friction angle, that is delta, the magnitude of tilt and shift will be reducing because it provides the resistance to tilting of caissons through action on the vertical wall of the caissons. So for a case when Q by V is equals to Q by V ratio as 0.5 and 800 kN vertical loading, as delta increases from 5/2 to 5, the tilt reduces by 18%, whereas shift reduces by 20%. It has been observed. Similarly, for acceleration coefficients, when Kv is equals to 0 and vertical load is equals to 800 kN, for Q by V is equals to 0.125, as we increase kh from 0 to 0.3 for a particular kh by kv ratio, kv by kh ratio is equal to 0, tilt increases by 136%, whereas shift rises by 64 times the initial value. So high amount of tilt and shift. Similarly, for kv equals to kh, for these loading conditions and the corresponding increase in tilt are around 98% and shift is around 65 times respectively, as we have seen from this particular figure over here. There was this case over here. It is for kv is equals to kh and this is for kv equal to this kv by kh is equal to 0 and this one is for kv by kh is equals to 1 for different combination of kh. For kh increases from 0 to 0.3. This particular figure on the other hand represents for different values of kh from 0 to 0.3, that is for the shift of the cases. Now, for different value map, how it will vary when kh remains constant for 0.1 and 0.2 and kv by kh rises from 0 to 1. It is seen that for kh is equals to 0.1, kv by kh ratio increases from 0 to 0.5, tilt increases by 1.46%, tilt shift by 0.5%, whereas from 0 to 1 it is around 2.9 and 1.3% respectively. So we see that effect of increase in magnitude of horizontal seismic coefficient is more prominent than increase in the vertical seismic coefficient. Both tilt and shift on caisson will increase with increase in kh value. However, the horizontal seismic coefficient will have a more effective play as compared to the vertical. Influence of the point of rotation. Depth of point of rotation of caisson plays a very important role in determining resistance offered by the soil. Higher the point of rotation, lesser will be the stability of the caisson, as the portion of the soil below the point of rotation will give reaction in the direction of the applied lateral loading. The variation of depth of rotation is shown over here. This variation is non-linear in nature, so larger magnitude of vertical load, it tends to stabilize the caisson, thereby causing the point of rotation to move downwards. But as the magnitude of lateral load increases, the caisson becomes less stable as reflected by the point of rotation moving upwards. So both the cases we have to see, because if we also increasing the vertical load, it provides stability to the caisson, but simultaneously lateral load is also increasing because it's a function of the vertical load, Q by V ratio. So that's why it will again move upwards, creating more instability to the caisson. Influence of the wall friction angle, that is same thing. We can say that higher the wall friction angle, lower is the depth of point of rotation moves further down with increasing delta, and hence improving the magnitude of delta will obviously add stability to the caisson. Why? Because the additional support provided by the caisson soil interface. Influence of the point of rotation by the seismic coefficient. It is observed that as the magnitude of kh increases, the point of rotation moves upward in such a way that the depth of point of rotation almost converges at Q by V is equals to 1. It is no longer be varying, it will almost be equal at this particular point. It is up. Okay, so it is observed that for kv is equal to 0, the point of rotation moves upward by 10.87% when kh increases to 0.3. However, at Q by V is equals to 1, the upward movement was around 7.23% respectively. Similar trend is also followed by this graph. It is noteworthy that because of the significant hydrostatic forces, the stability of the caisson diminishes as reflected by the higher movement, larger movement, upward movement in the point of rotation. Similarly, the same thing is observed for different variation of kV by kh. Its depth of pointer rotation moves upward for increasing lateral load. It more or less stays unchanged with significant increase in magnitude of KV. Thus, depth of pointer rotation also reflects that KH is a more important parameter in determining the deep of the case. Now we come to one of the important part of the current study, that is the development of the interaction curve. How we obtain the interaction curve already we have explained before. How we determine what is the value of my Vn already done, that is equals to 1000 kilonewton, and Qn also we have easily determined from that minimum base pressure graph. It is observed that the Q by V values required to develop minimum base pressure for the largest value of vertical load is around 0.4. Therefore, the normalizing lateral load Qn was taken as 0.45 Pn, and the normalizing moment is given by this term Qn into H plus T. Now, from this graph, I can see that we are having on x-axis V by Vn, one primary y-axis Q by Qn, and one secondary y-axis M by Mn, that is equals to M by Q1 into H plus T. What we see, it can clearly be seen that interaction curve for higher magnitude of delta lies at the top. This is represents for delta is equals to 4. Interaction curve for lower magnitudes of delta lies below and to the right of this curve. This indicates that for the same magnitude of vertical load, caissons with lower wall friction angle will fail at a smaller magnitude of lateral load, as we see from this graph. Conversely, caissons with smaller wall friction angle and subjected to small magnitude of lateral load or moment would require a larger amount of vertical load to prevent failure. This is because of the better load sharing in case of higher magnitude of failure. Same thing we have seen over here for different seismic acceleration coefficients. That is for kV by k is 0, then kV by k is equals to 1. For different kh from 0 to 0.3. Similarly, for kh is equals to 0.1 and 0.3 for different kV by kh from 0 to 1. So what we see from this graph, interaction for kV by kh equals to 0, 0.5 and 1. Interaction curve shift downwards and to its right as the magnitude of kh increases from 0 to 0.3. As we come over here, from 0 to 0.3, the curve will shift downwards. The negative magnitude of Q1M for kh equals to 0.3 indicates that load in direction opposite to seismic force must be applied a smaller vertical load itself to prevent the system from failing. That is, we have to apply a load in the opposite direction to seismic load force even at a smaller vertical load. Okay, that is its natural loads. Similarly, for varying magnitude of kh, the curves again move downwards and to the right as the magnitude of kV by kh will increase. This indicates the ability of the caisson to withstand the lateral load and moment has reduced for the higher magnitudes of kV. This is because at higher magnitude of kV, the vertical inertia force is diminished, which minimizes the normal reaction and causes the soil below to be in tension. The interaction curve for varying kh are more sensitive as they further apart than the interaction curve for varying kV. This highlights again the fact that the horizontal seismic acceleration coefficient has greater effect or bearing on safety of foundation than the vertical. So coming to the conclusions, we have seen that what caissons are a foundation system and have behaved rigidly as it is evident from the linear nature of the graph. From the same magnitude of vertical load, caissons with lower magnitude of wall friction angle fails at a smaller magnitude of lateral moment, and with higher magnitude of delta, it will be better suited resisting high magnitude of external force. Higher magnitude of wall friction angle stabilizes the caisson as it increases the load shared by the side of the caisson with base of the caisson. In the present study, this phenomenon has been reflected to maximum minimum base pressure till point of rotation and interaction curves. The depth of point of rotation of a caisson for a particular vertical load tends to converge towards the common point for all cases of kh and kv. The depth of point of rotation remains more or less unaffected by the variation of kv. Lateral load and including horizontal seismic force have a higher bearing in inducing yielding of soil than vertical loads. Lateral loading causes excessive displacement of caisson surrounding the caisson, causing the caisson to fail, as evident by the tilt, shift, and maximum rotation. Okay, so thank you for your patience hearing, and whatever, I don't know how much justice I could do, but I tried my best to discuss the various parts of new advantages, or rather say application of numerical modeling in geomechanics. By these three parts, pile and liquefiable soil, the application of surcharge loading, on sheet pile wall under hydrostatic conditions and the response of caissons to seismic. Now I hand over the session to the organizers. Okay. Oh, thank you.
Okay, thank you very much, sir. Uh, Thank you for your nice presentation. First of all, what I like to mention that normally this type of detailed discussion in the numerical modeling is not available in any net or any YouTube or any other platforms. Uh, Also, whenever this numerical modeling type of problems are getting solved by the students, they actually used to face some problems or doubts. Actually, from the student points of view, I want to mention some doubts. Actually, I want to clear some doubts from you
Yes.
on the behalf of the students before coming to the question and answer session, because there are several questions which are asked in the YouTube chat. But before coming to that, normally I want to address some common problems which actually students faced in whenever they are actually going to study this kind of numerical problems. Should I
Yes.
continue, sir?
Yes, please. Yes, please. Tell
Okay,
me.
sir. The first question is actually whenever this kind of AFM modeling or the numerical modeling is getting published in journals, normally the validation is a must. So,
Yes.
is there any experimental
यहाँ जाओ
validation
वहाँ
is
पे
necessary
ना
or any
just
analytical study? Yeah, sorry, sir.
give me 1 minute.
Hello.
Just sign one thing. Just a minute, please. Okay, just one
Okay,
minute.
okay, okay, sure.
थोड़ा दीजिए मेरा लेक्चर चल रहा है प्लीज फास्ट आपको करना है अच्छा ठीक है आप 12:30 बजे के बाद आ जाइए मैं आ जाऊंगा या प्लीज करिए आई एम सॉरी फॉर इंटरेक्शन डिस्टर्बेंस या प्लीज प्लीज कंटिन्यू यस
Okay, sir. Okay, sir, no problem. So whenever actually we are going to publish any AFM in any AFM study in any kind of journals, the validation is a must. So whenever the
yes
validation is going to be given, is the practical model is to be prepared or any analytical model can be done, or any literature review can be validated. That means if you give a general idea about what kind of validation is to be done in any kind of publication of numerical modeling, then it will be helpful for the student side.
हाँ see whatever you are saying the same problem I have also faced with my students because when we were sending that to journals now it was being rejected with the main condition that the validation is not being done. Now the problem is that for example this sheet pile wall, okay, sheet pile wall under surcharge loading and that too with seismic conditions you will not hardly will find anything in literature because sheet pile and this well foundation are some of the unexplored part yet because why sheet pile is mostly a temporary structure so people do not pay that much of attention. So whatever results at that point of time I had with the sheet pile wall derivations, that was basically done by this Madabushi and all in Cambridge University, and they have done basically with this either under surcharge loading or under a seismic condition, but both the things were not there. So initially when I sent these papers with either of the load and then I used to write a statement, the work is now extended to take into account the say the effect of surcharge. Then the reviewer used to comment, how can you say your mesh, that is the final difference model that you have made, will it be able to take the surcharge loading or not? How can you say that? That was the main problem. So what we did now, I also worked on the theoretical analysis, limit equilibrium based. In this particular presentation, I showed the numerical model, but the theoretical model also I worked on. That has been published in our ASC journal. So that theoretical model I worked on, and I validated my theoretical result with my numerical modeling in fact. And then that was the main validation. And then subpart also I did, that is for those cases where either surcharge is not there, but we are having a seismic condition or we are having the surcharge is there, but in static condition. So those are subpart I communicated to the journalist. But it is true because if every work is done in an experimental work, every experimental work is done, and what is the importance of my work? Where does the novelty of my work right? That also raises a question. So we have to be a little bit careful in analyzing this particular things. Okay. Secondly, one more thing I would suggest is that if you're doing any numerical work or theoretical work, always try to get it validated if available with field study or experimental study, because that always has a higher advantage. If you're not having, no issues. Because for my work also, I did not have any experimental work. There was some parameter that was lacking. So what I did was that from remaining work which I showed over here, I validated with a field result because I was getting something or the other. And then I changed my model by taking into account other parameters, flow of water, seepage and all those things, because those things are okay. That is an extension of your present study. Okay, so that is possible.
Okay, thank you, sir. One more question I would like to ask from the again from the behalf of my students.
Yes.
Actually, whenever we model the soil strata, not in any Plaxis or Flag 3D, in anywhere in any software, normally sometimes we assume them as a more failure model or strain hardening model, etc., etc. Now, is there any general guidelines that in this kind of conditions, this type of model can be assumed, they can work perfectly? Is there any general guidelines?
There is not that much of guidelines. Now thing is that it's a common principle we take into account if there is a molecular model. But if you see from the constitutive model, Morse model itself has got many limitations.
Yeah.
Okay. Similarly, two models that we have done shown over here. One was a liquefaction model. So for that, obviously, in liquefaction we cannot have a more model because it's the subgrade is reducing. It is degradation of subgrade model is taking place. So we have taken a brine model. So depending upon what is the condition, what is the problem we're analyzing. Say for clay, we have taken that in that Cason foundation. If you see the layered soil that we're having, the second layer, that is the sandwich layer, it is a saturated clay model. So for that, I have taken a camp clay. Obviously, because I've also modeled the flow of water through the porous medium, I've taken into account. So basically, depending upon the problem that you are analyzing, that you are modeling, I think the constitutive model accordingly has to be guided. But the problem is now in our education system, we do not have that many courses that takes into account this particular curriculum.
Yeah.
This constitutive modeling, although now in the IIT system, we are slowly developing courses on this constitutive modeling. So that's why I think a course on this is required. Different constitutive models in geotechnical engineering.
Okay, sir. Then, without wasting any time, I just want to hand over the session to Abhishek, Mr. Abhishek, because he will be conducting the question and answer session from the YouTube. Okay. So I'm handing
Okay.
over the mic to Abhishek. So Abhishek.
Thank you, Saurabh. Thank you, sir, for such a nice presentation. So I will take the few questions which is already asked in the YouTube live chat. So first question we will take from Mr. Ghulam Nabi, that is, in geotechnical engineering, how can I integrate a highly non-linear elastoplastic model within the FEM scheme?
Uh, Sorry, can you please repeat the question? How can we?
Yes. So in geotechnical engineering, how can I integrate a highly nonlinear elastoplastic constitutive model within the FEM scheme?
Okay. For this highly non-linear astroplastic model, I think it will be possible. If it is possible, you can take into account the various different numerical meaning that is available. Say in FEM, actually we assume an interpolation function is there. The Lagrangian, basically we take into account a Lagrangian interpolation functions. So using that and the corresponding this for this highly elastic elastrodynamic models, whatever equations you are having, if you can combine them, then you can solve. Actually, truly speaking, I have also not worked that much on these constitutive models. Okay, so basically the few things that I have done mostly is the molecular model and also this brine model and also the camp clay that I'm working on. So if you use this model that is available, that is the corresponding constitutive equations for the particular model, and if you can integrate it over the time domain in this FEM, that is by taking the Lagrangian interpolation function, then I feel, it's my opinion, that it can be solved.
Okay. The second question we will take is, when passive earth pressure may happen?
When passive earth pressure may
May happen.
happen. Okay. Say we are having a typical retaining wall over here. On the one side, we're having the backfill soil. Okay. And on the other side, we're having a wedge level. Okay. Now, because of some loading or something, we are applying a load. Okay, on this retaining wall or say it's a sheet pile wall, so what will be happening? Under the action of this loading, and since this sheet pile wall is like a flexible structure, it will be, about a point of rotation, it will be moving away. So because of this applied external loading from the lateral side, this will move towards the backfill. This will move away from the backfill soil towards the soil and vegetable side. And in that case, the passive condition will be encountered. Actually, truly speaking, passive is generally the force. Passive, the passive will be, this sheet pile one will be moving towards this backfill soil. So we can say that this backfill area is in a passive condition because of the applied of the lateral loading. That is, passive is experienced resistance and active is generally the force.
Thank you, sir. The last question which we are having, that is, at the beginning, homogeneous fourth order ordinary differential equation can be solved using any weighted residual method? If yes, then how?
Uh, this question actually it's a bit difficult to explain the procedure of weighted residual method. Is that if you go through any typical finite element book, those are the basic things. That is, you have to divide into small elements and take into account that weight of this, that is A and B are the two divisions. Because now at present I'm not being able to recall the exact procedure of it. I'm sorry for that.
Okay, so the next question is there, that is, in case of seismic analysis for pile raft foundation based on numerical modeling, as you showed, how the validation part can be done if experimental studies not available?
Pile foundation, plenty of studies are now available. One of my colleagues, Dr. Professor Ashutosh Kumar, who is now in IIT Mandi, assistant professor, he also did his PhD with Professor Dipankar Chaudhary from IIT Bombay. He has worked significantly, his entire PhD thesis work is on that, and he's already published plenty of papers in soil dynamics, earthquake engineering, computers and geotechnics, AC, IJOG, then this IC geotechnical engineering. The plenty of papers are available. Please search the literature, you will be able to get it.
The last
It is
question which we
available
are
in
taking,
literature.
thank you, sir. So the last question we are taking, that is, in liquefiable zone, which pile would be better, pile foundation or caisson?
Which pile?
Would be better, pile foundation or caisson?
See, pile foundation and caisson, although both are both of them are two different type of deep foundations, but generally, in case of a liquefiable zone, the portion of the pile foundation or caisson, whatever is passing through them, they will be not be having any shear strength. So your site resistance will almost be equal to zero. And it depending upon the condition, say if you're having a bridge pier, for that case only, we are now going for a caisson foundation because of its strong rigidity. Okay, whereas generally if you're having a building or a multi-story complex, for that case obviously we'll go for a pile or a pile raft foundation. We'll not go for any caisson foundations.
Okay, thank you. That's all the questions which we are having from the YouTube live chat. So thank you once again for answering or responding to all the queries which
And
has been
one
asked
more
in the
thing,
YouTube.
that regarding the weighted residual method, exactly at present I'm not having that idea, but generally for any basic finite element book, if you go through, those are the basic thing that is given over here. That is, we divide into elements and we take the weight of each element and do some, I think, actually I'm completely out of touch with that part.
Thank you, sir.
Thank you. Thank you.
Okay. So thank you, sir. Thank you very much. We're at the end of the session. So we have to conclude this. Sir, I would just like to thank you for your wonderful presentations, and I would like to propose a hearty vote of thanks to you for staying here, for sharing valuable time with us. And last of all, I would like to express our gratitude to our principal sir as well as our HOD sir, also to our organizing committee, and finally the participants. Now, at the conclusions for the participants, again I'm repeating the one thing which I'm going to repeat in which I actually used to repeat in several webinars that at the description of this YouTube video, there is some feedback form is being given. So please fill up the feedback form within 3 p.m. of today to get a certificate of participation. Unless and until you fill up the certificate, unless and until you fill up the feedback form, we will not be able to give you the certificate of participation. So thank you for staying with us. Take care, stay safe. Thank you. We are looking forward to meet in our next webinar. So thank you very much. Have a good day.
Okay.